Okay, we left off talking about right before lunch where we're going. We're going to do normally open, normally closed solenoids, right? And then we're going to talk about that guy, and then we need to talk about the variables, and I want to show you some more stuff on the car which will help emphasize all of this. Let's talk about this one real quick. This design is not very common, although it's becoming more common. So GDI systems, we'll start with that, gas direct injection. This is how all their injectors are wired, that both wires go to the computer. And on gas direct injection systems, we will never manually energize these. Okay, so let's start with that. There's going to be circuits that I don't want you to manually energize. And by manually energizing this circuit, again, let me back up. If we manually energize a circuit with it still connected to the computer, you guys understand the dangers involved. So let me back up even further. That gave me a thought here. Like if we did it this way, remember we fried the computer here, and if we do it this way, this is a power side switch. We fried the computer if the driver was on. You guys remember the discussion. So some of you may be thinking at this point, why don't you just disconnect the coil and then run your own ground and, let me get a different pen. Why don't we just disconnect the coil and give it a ground and give it a power outside of the circuit? That's completely acceptable, however, not practical. In the real world, you cannot get to the solenoid to do that. The location limits you to doing that. Now, if that solenoid's up in the open, you can do it that way if you want. The reason I'm teaching you these methods is I want you to test that solenoid where it lives. For example, I say a GM vent solenoid that's tucked up in the wheel well area. You can't get to that solenoid unless you unbolt it and bring it down to work with it and then do your check, manually energize it, see if it works. That's what the manufacturer wants you to do. And the problem with that is those solenoids stick, and in the process of you unbolting it, you've unstuck it. So when you check it, it's going to test fine. So are you guys on the same page with me with why I'm teaching you to use the circuit? Don't touch the solenoid, test it where it lives. That's my thought process through this. Okay, so just so we're clear, I am not telling you that we can always energize these things within the circuit itself. We can energize them outside of the circuit. It's much safer. I just gave you an example of why we want to energize it within the circuit. But even with that being said, certain circuits we don't do this on. One of them would be a gas direct injector. Okay? To stay on the injectors here for a second, we don't do this with any injector. If you want to check an injector, we're not manually energizing it. There's other tools we use for that. That would be the one solenoid we're not going to manually energize. You're going to hydrolock that cylinder if you do that. And the other thing you can do is overheat the injector windings on some of them, and we definitely wouldn't want to do it on GDIs. GDI systems will control both sides of the injector, power and ground. We'll cover more of these later when we get into section 17, our injector circuits. Stay away from GDIs as far as any kind of manually energizing within the circuit. So that being said, is there other circuits that might be like that and we could hurt the computer? That's where I'm going with this. We could hurt the computer if we do this wrong, right? So we don't want to do that. What I've found with a lot of them, not the GDIs, up until GDI systems, all of the solenoids that I've seen like this, the computer controls the power side of it, and it is internally grounded. So it's really no different than this one. Why are they doing that? I don't know fully, but I will tell you that this bottom circuit can be monitored. This bottom circuit can be monitored for opens and shorts easier than the top circuit can. That's why they run that ground inside the computer. I would say if you see this design, well, first thing is, we don't know the internals, so which side's which? You give this the wrong polarity, you're going to hurt something. Agreed? So maybe when we see this design, we should probably not use the circuit, unplug it, and manually energize the solenoid if you feel the need to. There's ways that you can do this, and this is how I would do it, and you can adopt this if you want, and you don't have to if you don't want. But what I'll do is, I take my 2 voltage readings, of course. I have 0 and 0. Next thing I'll do is unplug it, and I'll take, just like we did before, I'll take a test light here to battery positive, and I'll take a test light here to battery positive, and it'll light on the one side, even though it's going into the computer, it'll light, and that's my ground wire. The other side's my control wire, and I can safely give it power. So I've done that. In fact, I have a video on doing that on an EGR system. I don't remember the exact video. It was a GM EGR. They changed their controls on the solenoid for that. I think with this one, probably the best thing to tell you is if you see both wires going to the computer, I don't want you guys putting any kind of jumper wires in there at all, just to be on the safe side. Questions? We're going to see a lot more like that, so I don't want to blow past it. Okay, I wanted to do this faster, and I don't think it's going to happen. Because as I was talking, I realized I missed something. And what I missed is diagnostics. I mentioned to you guys that the computer monitors these. And that's the first time I said that to you. We need to cover that too. Now, do we want to do that now? It's pretty complicated. It can get complicated. Now, let's do that later. You guys need to write on your list of things to cover. And this is the downside of not following page for page out of my book right now. A list of things to cover is diagnostics on these circuits. Okay? We need to cover that. It's really important. So we'll come back to that. And to get away from this, if we run the ground inside the computer and we have the feed inside the computer can more accurately monitor what's leaving, what's coming back on this circuit. Let's just leave it at that for now. And that would explain why they didn't just run it like this one up here, where we're just sending voltage out on this power side switch, externally grounded. This one down here is a better circuit for monitoring for opens and shorts. Can you guys accept that at that level for right now? Yes.
What's it called? Like the ones that open sided switched? Or the...
What's this? I would still... Good question. What's this circuit called? I would still call this a power side switched circuit. It is absolutely no different than this one right here. They work identically. The only difference is where that ground is. On the one above, the ground is external, and on the one below, the ground is internal. No difference whatsoever.
You're only going to see that on a schematic?
Yes, but here's what the schematic looks like. Computer, solenoid, wire, another wire. That's it. That's all you got. If you see that, most likely, other than GDIs, that is a power side switch circuit. Let me say this. Here's what I can say. I have never seen a solenoid wired like that was ground side switched. Does that help? Okay. Now that doesn't mean there won't be one somewhere. I just haven't seen it. We got to come back to the diagnostic part. I want to do normally open, normally close, and to do that, I need to go to my book because I drew a picture that will really help us. And this is a perspective we need to have right here on page 7. Solenoid state electrically is not the same as solenoid state mechanically. Should I say that again? I'll restate it. And a solenoid that's electrically on can be mechanically off. And a solenoid that's electrically on can be mechanically on based on the internal mechanics of that solenoid. I drew 2 pictures to show you that. One of them is called a normally open solenoid. The other is called a normally closed solenoid. Okay? The picture to the left, we can see a normally open solenoid, meaning that there is a spring, and I'm showing this picture, there's a spring here that's forcing this plunger into this position, and so the passage between these 2 ports is normally open, meaning no current flow up here on the electronic port, no current flow, no magnetic field. That solenoid's going to have flow through it. So the solenoid electrically is off, yet mechanically you could say that mechanically that it's on. I don't know if you want to call that on or not, or there would be flow through this, on or flow. And then if we turn the solenoid on electrically, we give this a magnetic field, we pull the plunger up inside and we move this thing to a place where we're blocking flow. We could say that the solenoid is off or no flow. Okay? Picture to the right, it's completely opposite. We have a normally closed solenoid, meaning no current flow. Electrically, we're off up here. We are off down here too, mechanically. Turn the solenoid on, give it a magnetic field, and we pull this up to this position, and we are on here too. We could say off up here. Does that make sense? Is this a perspective you need to have when you're working on a car and you're working on, say, an evap system solenoid, and you want to know if that solenoid should have flow through it or not, and at what point in time should it have flow through it? A vent solenoid for evap systems are normally open. So if you were checking a vent solenoid on an evap system, what you would do is to clear this drawing, it won't let me. What we would do is we would normally open it. We would attach a rubber hose to this, and we would blow air through this, and we should be able to blow air through it with the engine off, car off, solenoid disconnected, whatever. Next step you would do is you'd energize it, and you're blowing on that same piece of hose you attached to that, and you shouldn't be able to blow through it. So we look for a change of state when we energize the solenoid. When I say change of state, so if you go through the text in here and I say energize the solenoid and listen for or look for a change of state, do you know what I'm talking about? If it's normally open, what just happened? It closed. If it's normally closed, what just happened? It opened. If it's a hydraulic solenoid in a transmission, Kevin, you're not going to be blowing through them. What you're looking at is pressure changes on either a gauge or on the scan tool. Okay? If you're working on an evap system, maybe we can put a vacuum gauge on one side of the solenoid if it's a purge solenoid and command it on and see if we have vacuum now where we didn't have vacuum before. There's different ways we can confirm a change of state. Actually, what we could do with a purge system is we could pull the oxygen sensor up on scan data and a bidirectional control and turn the solenoid on and then watch your O2 go rich because we just opened the purge valve. So there are different ways to confirm change of state. Yes. All right, let's do this. With the information that I've given you so far, I want to take you back to the car. What I want to do is I want to review some of the stuff we've just been talking about. I want to review circuit identification. I want to review energizing the component. I want to review solenoid design, normally open, normally closed. What I want to start with is this Egr solenoid that's on this car. Let me get this test light out of the way. Where am I looking? Right here. This is an Egr solenoid on a Chrysler. I know this is a Mitsubishi, but it's a Chrysler setup. So we have a 2-wire solenoid that sits on top of here, okay? First thing that we're going to do would be let's turn the key on and get 2 voltage readings. What will that tell me? What am I looking for with these first 2 readings? Rich, can you turn the key on for me? Very good. Identification's what I'm going after here. Now, do I need to be careful with my T-pin? Yes. I definitely want to be careful with my T-pin. I don't want to touch in anything metal. I'm only going to use one, okay? So voltmeter, look what I did. I did a no-no, and the last thing I did on the voltmeter was what? I left my probe in the amp port, and if I forgot and I am now switching to DC volts, right, that's what we're about to measure. A lot of people think, well, you're okay now, you're measuring voltage. No, internal to this there's no resistance. You're holding in your hands a jumper wire. If I connect this up, I will blow the fuse in this meter, so that's why I put fuses in them. People do it all the time. When you're done over here, move this back over here. We're going to do voltage measurements now. Okay? My preference, again, I don't like the beeping that these meters do, and it's on an auto range scale right now for voltage. I don't like that. For everything we do on the car, pretty much, if you set your meters to a 0.00 scale, that's perfect. There's your 1 scale, there's your 10s. This would be your hundreds of millivolts. That's your tens of millivolts. That's good enough. We don't need to read hundreds for millivolts. That's a pretty small number. We're not too worried about that. That's a perfect scale for just about everything we do right there. All right, since we're doing this, another thing that I want you guys to do is I'm taking this out of this insulation too. I hate these rubber sheaths. They're useless and they get in the way. You can put it back if you want to. Now some people like them. Here, I'll show it to you. I don't like these. I don't like these rubber sheaths. They get in the way. I mean, they will help protect you from certain things. So some of you guys like them. I always take them out of there. I prefer that. It's a lot easier to work with. And we're about to do some voltage measurements, okay? And what we don't want to do is we don't want to do voltage testing that would be like this. So you're grabbing the 2 leads and let's say, I'm going to connect this to, this isn't a ground, but just so you can see it in the camera. I connect this to ground and then I do my checks on my solenoid. Do you guys realize that every time you move this ground, you have to rethink to yourself, is this a good ground? So what you want to do before you do any kind of voltage measurements is you want to connect your lead up permanently to a ground. That's why I prefer an alligator clip, so I'm now clipped to the battery. Next thing I'm going to do, am I ready to check the solenoid? Absolutely not. The next thing I'm going to do is I'm going to check my meter by connecting to the battery. So I'm just touching on the battery right now. All right, so my meter works, right? You guys were probably taught to check your meter. And as I've stated to you before, we know the meter works. Why are you checking the meter? We're not checking the meter. That's the wrong perspective. What am I checking? I'm checking the ground for my meter. So if that's what you're doing, should you relocate your ground now? This is what I see everybody do. Check your meter. So you come up to the battery, you check the meter at the battery, and then you say, okay, my meter works, and then you go back to the taillights and you're working back there. That didn't do you any good. Of course your meter works. It's been working for the past 20 years. It's a voltmeter. They never go bad. I've never seen a voltmeter go bad ever. So what are we checking? Connections. I want to know when I put this positive lead to something that if I read 0 volts here, that is a true 0 volt reading. and not a 0 volt reading because I have a bad ground because I relocated my ground. Can I be comfortable right now with my ground? Yes, and I'm not touching it. Notice my hands are not on the lead. I don't want to see you guys two-handed testing things. And by two-handed testing, meaning you're holding the black lead in one hand and the red lead in the other. If I see that, if I was a nun back in the day and I had a ruler, I'd smack your hand every time I'd see it. Okay? Don't do it. Put your alligator clip on there. In fact, if you look at any one of my multimeters, I have a alligator clip on my leads all the time. That's where it should be. All right, anyway, a little rant there. Okay, are we ready to test the solenoid? Yes, we are. Is my key on? I don't think it is. Rich, did we turn the key on? Okay, good. Battery voltage is a little bit low, but no big deal. We'll be able to do what we're doing here. So I'm going to back probe this solenoid one at a time, being careful with my T-pin, going in straight with the pin. If it doesn't go in straight, remove it, go back in again. And what I want to do for this is to connect my meter. And I guess, you see this, I'm taking this one off too. These drive me nuts. Do I need to be a little bit more careful without the insulation on that? I do. But stay on here nicer. Clipping to this first pin. What do we have? 11.27 volts on that wire. Do we know anything yet? No, not yet. All right, let's go to the other wire. .19. This is maybe something that we didn't expect to see, because we were thinking we were going to see 12 and 12 or 0 and 0. Is that where everybody's head was? 0 and 0 would have been what? What design? Remember, we're not troubleshooting yet. We're just circuit ID. We're just circuit identification. No. There's two different types of solenoids, power side and ground side switched. If it was a power side switch circuit, we'd see 0 and 0. If it was ground side switched, we'd see 12 and 12. We're seeing 12 and 0 right now, agreed? I know it's not exactly 0, but this isn't what we expected. Well, that sucks. So when would we see 12 and 0? Well, either here's what we have. Either there's a problem in the circuit, or the circuit's already on. How do we know that?
You turn the key on.
All right, the key's on, but that doesn't mean that solenoid's going to turn on. And I like that thought process, but this one's unique, and I chose this car, and this morning when I looked at it, I'm like, all right, perfect. This one's perfect for what we're doing. Let's come back to, this is part of what we're doing here too. Let's come back to this for a second. We have a solenoid that we're unsure of really anything with it, right? Just a kind of a box here, and we have a connector, and we're back probing, and we have 12 volts and we have 0 volts. If the circuit's on, would you agree with me that there would be then a ground on this wire?
Yes.
Okay. Is there a quick way that we can identify that, if we have a ground on that wire or not?
Could you unplug it in your test light and plug it?
Yes. Very good, Nick. I don't need to unplug it, actually. I can just use, and it doesn't really matter for this if I use an LED or an incandescent light. I'll use the LED light, and I'll connect it to ground. And here's what we're going to do. We're going to take this, connect this light to, not ground, battery positive. If this light lights, what's that tell me about this 0 volt reading? There's a ground on that circuit, as opposed to if it was like this. Say it's ground side switched and the circuit was off. You guys would agree with me that this should be 12 and 12, right? If that circuit's off over here. So if it's 12 and 0 with this circuit off, what would cause that? Very good. A short to ground on this circuit would do that. What else would cause this? This is all the other stuff that I have listed in section 3, by the way. An open where? Did you say an open?
Yeah.
Very good.
Between,
An open right there in the coil itself.
yeah.
Yeah. So there's faults that we could have this problem, but there's no problem with this car. So let me show you the test back on the car. And I do this a lot in troubleshooting too, and finding out a circuit that's 0 volts and it shouldn't be. So I take my test light to battery positive. Kind of zoom out a little bit here so you see the battery. Test light to B plus. Okay. And then when I find a ground, I'll just touch something metal here. This test light should light. Okay. Touch on that T-pin. It's lighting, which means what? That solenoid's grounded. All right. Now we have to rethink our process here. This is an EGR solenoid. And is there a hose on this car? And is our exhaust fan on? If you put your hand on the pipe back there, you'd be able to feel it if it's on. No? Okay. I'll go turn it on. All right, we're going to start the car. I moved the voltmeter off of the exhaust manifold, which is probably a good idea when you think, Nicole. Leaving your voltmeter sit on the exhaust manifold is probably not a good idea. Start this for me, please. All right. It's an EGR solenoid, okay? An EGR solenoid, we would think, with the car running, that the solenoid should be off because we don't want any EGR at idle. This is the perspective you're going to have. Yet, take a look at that voltmeter. What are we reading? Low voltage. Let's take a look at that test light again. What are we reading? A ground. That solenoid is on right now at idle. The EGR solenoid on this car is on at idle. That's weird, isn't it? If we go to the scan data, let's pull that up. I'm building on something here. I may have gone about this the long way, but bear with me. I'm going to go to scan data. I want to find this EGR solenoid on the scan tool. I remember the first time seeing these, it really threw me for a loop. Looking for my EGR solenoid. EGR command is off. See right here? I don't have one that says EGR solenoid, but this will still work. All right, that's kind of contradictory, isn't it? We just found a solenoid that's on, and it says EGR command is off. Well, what if off was on? What if CAT really spelled dog? Sorry, Lenny, you said what?
Is that normally closed?
Close. This is a normally open solenoid that we need to energize it to close it because we don't want any EGR at idle. Solenoid is on to block EGR flow. All right, so I'm teaching you what? In this section, I want you to be the computer, energize the solenoid, watch for a change of state. You guys follow? So how are we going to do that here? I can't take a test light and de-energize it. Because isn't that the perspective we need to have right now? If it's already energized, I need to de-energize it to change the state. What am I going to do? What? Open the switch. Well, that would work, but the switch is inside the computer. Can't open that transistor to turn it off. Bidirectionally, I could. That would be one way, but let's say we don't have a scan tool. What? Unplug it. If I unplug this, that, you won't see any reaction up here. That solenoid is now de-energized. And if I open the throttle on this a little bit, you're going to find that we have vacuum now available to this EGR. It's a ported type vacuum. That's why you didn't hear a change. Let me show that to you. Let me get my vacuum gauge. Get you back up here. By the way, these older systems, what threw me off, and I was hoping to show you that on here, what threw me off on the scan data, the older systems would say EGR solenoid on, and I knew the EGR valve should be off at idle, and the solenoid state said it was on, and that was confusing to me as a rookie. Can you guys understand why? I didn't understand the concept of normally open, normally closed solenoids. All right, look. This one's a little goofy, and I don't want to go into back pressure transducers right now, but that's what this is. The way it works, just briefly, is what we have. Take that off. What we have is a vacuum line right here that comes in where my middle finger is, and a line. This one goes to the. Sorry, let me back up. This one comes from the manifold. It's ported vacuum. Actually could be intake, and then goes to the EGR over here. But for this to occur, there's a port underneath that has exhaust gas, so it uses exhaust pressure to close the diaphragm to allow flow through. So what I want to show you is the valve working. Watch. Take the hose off to the EGR. Maybe. Yeah, just so you can see the difference with the solenoid plugged in and unplugged. And it's pretty hot. If I could stay here or not. You see that vacuum gauge? Solenoid unplugged, watch. I rev it a little bit. That's that back pressure transducer working, exhaust gas closing the diaphragm, giving more flow through. That's with the solenoid de-energized. Here's with it energized. Just plugging it back in. What do we see? I'm going to rev it again, watch. That rev, the computer was turning that valve on. But at idle, I didn't expect to see that. Watch. Test light. Okay, you see it? Test light's lit. Watch. I stated that wrong. With it plugged in, you see it idle, there's nothing. You see it's blocking it. And then what you also saw is when I revved it, the computer was unblocking it by doing what? Not energizing it, I stated that wrong. By doing what? De-energizing it. Test light, now watch my light. Test light's connected to battery positive, right? Where's that ground coming from right now? The computer's grounding it to close the solenoid. Rev it up, when this light goes out, we lose our ground. Computer shuts the circuit off. All right, shut that off. I changed my mind, start that back up. One more thing. So you're working on this car, you don't have the ability to bidirectionally control that solenoid. Maybe the scenario is you're revving it, nothing's changing. You want to check just the solenoid, see if it functions. What do? Unplug it. Unplug this one to change its state. So do you understand the approach? Let me show it to you one more time. I'll unplug it. Watch the vacuum gauge. Now the reason we don't have full vacuum is the way the transducer's working underneath. In fact, I could blow on the transducer underneath and make that vacuum go up high. This would be how you check a transducer. A little bit different subject, but you guys understand that if you want to force this solenoid to change state, that unplugging it is how you would do it on this design. Why? What type of solenoid is this? Good, shut that off. What type of solenoid is that? Is it normally open or normally closed? It's normally open. Normally closed solenoid, you want to change its state, you need to energize it, right? Yeah. Normally open solenoid that's being turned on already, you want to change its state, you have to de-energize it. So you understand the approach is different depending on the solenoid itself, mechanically. Where is this information? I have it. You have a normally open solenoid that's being energized. This is actually a test question too, so pay attention. You have a normally open solenoid that's being energized. How do you force it to change its state? A, with a test light. B, unplug it. C, scanner bidirectional controls. Or D, both B and C. D, both B and C. We can do it with the scan tool. We can do it by unplugging it if it's already being energized. Okay? Questions? So the 2-wire one to the computer, we covered that. The normally open one, we covered that. What else did I say we need to do? Diagnostics, and I'm not doing that one yet. We need to break first. One more piece I can show you is, and this is all in here, this would be solenoid functional test. We did that. We talked about the warnings and how to handle the circuits properly. Testing computer drivers and control circuit integrity. Let me show you this one real quick. This page, we can follow the text, of course, but I'd rather show it to you live. So let's go back to our car here for a second. And you guys saw when we were messing around with this that I could make the test light turn on and off with revving the engine. So what was changing? The driver in the computer was changing things. Is that one way we can do this? Can we make that driver turn on and off by external inputs? RPM, throttle angle, possibly.
Yes, should be able
What if you can't? Scanner bidirectional controls. Well, what do we know about this solenoid? We know it's ground side switched. The circuit happened to be on all the time. If we have the key on this, I think this was on, right, before the circuit was on. We can do this unplugged, plugged in. I'd prefer doing it unplugged to prevent any kind of incorrect or backfeed. Test lights to battery positive right now. Can you turn the key back on this for me, Rich, please? You see the computer is energizing this, and I'm actually just going to kind of do that so you guys can see it while I'm commanding that circuit on and off. I'm going to go into the scan tool, and I'm going to bidirectionally turn this thing on. So I go to my functional tests, I go to ATM tests. Sorry, not turn it on, it's already on. And what I'm going to pick is my Egr Solenoid. Can you guys get a visual of that? I want you to focus on the test light. And then I'm just clicking the on button here. As soon as this loads up, click the on button, click the off button, click the on button, off. Now that's kind of weird, right? Off is on is off. Remember, it's a solenoid that's being turned on all the time, so this one's weird. This isn't typical. So how is the wire, now you think about it from a manufacturer standpoint or from a flowchart standpoint, where they have you disconnecting the component and measuring resistance and all this crap. I don't need to do that. If I have this kind of ability and I understand circuit design, I understand it's ground side switch, so I put my test light to battery positive, and I take the scan tool and I bidirectionally turn it on, and the light lights, and then the light doesn't light when I turn it on and off. Is the driver functional right here? It is. And how is my wire from the computer all the way to that component? It's good too. It's good too. Any concerns of test light current here with this test?
What do you mean by test light current?
Well, how much does this solenoid normally draw? And how much current flow does your test light draw?
Would you say like 300 milliamps?
This solenoid's probably close to 300 milliamps. We could do a measurement. Maybe I'll do that when you guys are on break, just to measure it. Is either test light going to be a problem here?
No.
Nah. I'm comfortable with my 200 milliamp test light. I'll show that one to you. Take this LED one out. Although when you're checking computer drivers, if there's any concern, wouldn't the lower test light one be the one to use for checking the driver? Yeah. And wouldn't the higher test light be the one you'd want to use to energize the solenoid? Remember when I energized the relay earlier, the LED one didn't work, and my incandescent one did. Now that we're checking the driver, if there is concern, use the LED one to check the driver, use the incandescent one to energize the solenoid. I'm telling you though, this 200 milliamp one, you're pretty much safe on anything I can think of under the hood. This is more than what that relay draws, but they don't just put a transistor that can only handle the current that's in the circuit. That would be dumb, because you can have spikes that would kill it. They can handle way more than what the circuit is that they're driving. So you're pretty safe with this one too. Watch. There's my incandescent light. I'm not worried about this. Remember, it's about 200 milliamps. But, you know, we as mechanics, we tend to be creative. And when the bulb burns out in our incandescent test light, we just grab a bulb in our toolbox that fits and we throw it in there, and if it works and lights, then we use it, right? If you're going to do that, do you think you should recheck the current flow of your test light? I've had test lights that I threw a dome light bulb in, and they would draw like 800 milliamps. It was a drop light under the hood when it would light up. I could literally use it as under hood light. Do you think that might be a problem on a relay driver that's low current? Let me jump back to that for a sec. Can you shut that fan off and close those doors for me? Let me jump back to this relay real quick. Let me show you this one more time. This relay circuit relay was ground side switch. We didn't do the diagnosis of that. You're just going to have to take my word on that. So I'm going to connect my test lights back to ground to energize the relay. We'll do that one first again. I'll let you guys break here after I do this. The incandescent light on the relay circuit, which was, let me get my bearings here. Is the key still on? It was this one. Okay, listen to the relay. No problem energizing that circuit with this test light, right? That would be the computer driver. Here's the LED one. No good there, right? Okay, so let's say that this car came in, and remember it's that one right there. Let's say this came in and this relay was damaged, it was destroyed, it was in an accident, okay? And so it's a ground side switch circuit. I'm going to back probe this again. This scenario again, the car was in an accident, it was hit, it was crushed. Is it possible that, we know we need a relay, that's beside the point, but is it possible the computer driver got cooked in the process of these relay getting smashed and these wires shorting out together? Is it possible the driver's cooked in the computer? Yeah. Yes, okay. Another scenario would be that Egr solenoid that I showed you was laying on the exhaust manifold, completely melted. Look, you know you need an Egr solenoid. Question is, how's that driver? Do you sell the customer an Egr solenoid first? $100 part maybe, because that comes with a valve. Maybe it's $150, only to tell them when you're done, I'm sorry, you need a $700 computer too to fix this Egr code you have. Isn't that something you should tell them up front? You need both pieces now or nothing. We don't just do one and then say, well, forget it, I don't have 700. I had the 150 for the valve. I don't have the 700 for the computer. I would have wanted to know that up front, so I could have made that decision. So this is where I get angry with people in my field that say you should never use a test light for a computer-controlled circuit. Really? I should never use a test light for a computer-controlled circuit. Think of the scenario that I just painted for you. Relays crushed and destroyed. Egr solenoid's melted. We can't use the solenoid or the relay to see if it's working. What are we going to substitute it with? A test light, if you know circuit design. This is a ground side switch circuit, so where should my test light be connected? I'm not energizing the solenoid here. I want to know if the driver's good. What does the driver do? It grounds the circuit. What's the polarity of my test light? We are intentionally going to put this to battery positive. Okay? I'm on the fuel pump circuit, my fuel pump relay. Looks like that's glowing a little bit. That's the misleading part of LED lights. I'm going to go to my fuel pump relay and I'm going to turn it on. Turn it off. Turn it on. Or is that my ASD relay that I was messing with? It might be. Hang on, let me see. I assumed that was the fuel pump relay because of the pump. I heard the pump run. Hang on. That should have worked.
Is it because you're using the LED one?
It shouldn't be. No, that's the ASD. No, that should have worked. I may have. Let me try it one more time. That was definitely the fuel pump. To exit and leave actuator test running, select resume. To exit, turn actuator off. Select exit. All right, exit. Fuel pump relay circuit. All solenoids and relays. Well, pretty sure that was a pump running, wasn't it? You guys heard the hum in the back, right? This should work. Am I not making contact? Oh, that was it. Oh. Hang on. Too much crap here. Okay, it's a pulsed circuit. What? I just wasn't patient enough. I forgot that Chryslers do their, when they cycle it with the on off, it isn't, you turn it on, it just stays on, it pulses it on and off. So in this scenario that I just gave you, how's the computer driver? How's the wiring in this accident or melted valve? Are we good? All right, so what if you did this test and this didn't work? Is there further diagnosis we need to do before we put this valve or relay in here? We better make sure we don't have any other wiring breaks. We have a very real chance of having a driver that's destroyed. So do you understand the test light's my friend here? All right. Do you understand that the LED test light for the drivers is really the preferred test light? We're at 13 milliamps. Trust me, you're not going to hurt a computer output with 13 milliamps. All right. Is there an issue with the incandescent light? Is there a possibility this incandescent light, if I go to battery positive, that I could hurt this relay circuit? Just to show you how confident I am in this circuit, I'll throw that one in there too. Relay coil current's about 100 milliamps. Am I putting more than 100 milliamps in this circuit now? I'm putting about 180 milliamps in this circuit. So is the, again, LED test light the better tool? Yes. I believe if you stay under this 200 milliamp number though, you can pretty much use the incandescent light just like you would the LED. The only thing I can think of that might be lower current, I'm thinking of an idle air control valve that's about 40 to 50 milliamps on the idle air control circuits. I would probably want to use the LED one for that, but man, I've even used the incandescent for those ones. Do I know a number of what the transistor can handle? I don't. I know fuses, when we fuse protect a circuit, we run a fuse, or we run the circuit at 80% of what the fuse is. So if it's a 10 amp fuse, the maximum that circuit will draw is about 8 amps. So do you think drivers are the same way? We don't just, you wouldn't put an 8 amp fuse in an 8 amp circuit. You're going to blow that fuse sometimes. Drivers are the same way. I don't know what the number is. And maybe our next car that's going to the junkyard, we could keep playing around with it and see what light we could put in there and what current flow we could put in there to burn that driver up. That would be fun. If I do that, we'll film it and we'll throw that up. That'll be a good one to do. I'm comfortable with this light. Is the test light your friend when it comes to checking computer circuits?
Yes.
Yeah, I don't know what people were talking about. Don't use a test light on a computer circuit. What are you talking about? This is the tool to use in the scenario that I just painted for you. Now, of course, we can, use other senses too. If you're doing a bidirectional control, you plug the relay back in. Take a listen. Is that good? You hear the sound of the relay clicking on and off? Let me get close to it so you hear it. Okay? How's that sound? What's that sound tell you? The relay's energizing. I can hear the pump running too. Multiple ways to do things. Questions? Bidirectional control. It's pretty cool, isn't it? Scanner with bidirectional controls. A guy with a little bit of knowledge of power and ground side circuitry. Normally open, normally closed circuits. current flow, identification of the circuit. Man, you are armed with a ton of information, and you can do very fast troubleshooting. Why does an engineer flowchart have you disconnect the computer, disconnect the solenoid, disconnect the relay, and ohm check the wire? Are you kidding? I'm actually going to look up the flowchart, see if they have one for this fuel pump relay when you guys are on break. I want to see what it is. When you guys come back from break, we'll talk about a couple more scenarios of direction, the variables, and we'll plug in the bias voltage stuff and the computer circuitry tomorrow at some point in time. I still want to test you guys. I don't take a break and I'll think about what else I want to cover with you.